Welcome to Architectural Insights with KING-KAMBUF. We are jumping straight into the strategic intelligence from the services of KING-KAMBUF PS Architecture, specifically their daily interdisciplinary mentorship brief, which came out this morning, Thursday, December 4, 2025. And what's really striking about this document is that it's not just about, successful construction. It's really about anticipating the next decade of failure points in the built environment.
It really is. It's mandatory reading for anyone who's aspiring to what they call world-defining architectural and infrastructural leadership and the foundational shift it demands. It's huge. The material makes it so clear that the traditional model, designing these static structures based on predictable historical load paths, it's just dead.
It's over.
It's over. We now have to design dynamic, sensing, and highly responsive systems.
Absolutely. And when you synthesize all the global data points in these briefings, the message is, well, it's uniform. Every single fundamental assumption we held about structure, air, water, heat, vibration, it's all being fundamentally challenged. And that's driven by climate extremes and these incredibly complex new building programs. So the goal of this deep dive is to synthesize all of that data for you.
And that's the mission, right? We're trying to bypass the general best practices you hear everywhere. We're moving directly into the highly specific, often invisible loads that are going to define success or failure on major global projects.
Okay, let's unpack this. We need to establish the new global challenges that are reshaping design philosophy from the ground up. Then we'll analyze the unexpected dynamic loads that come from modern architecture, everything from chemistry through acoustics. And then we connect all that back into how architecture itself is becoming a form of, well, civic and atmospheric intelligence. Let's start at the very bottom, literally, with what KING-KAMBUF calls the new environmental load path. The Earth is moving, the climate is volatile, and our old methods for, securing buildings, they just aren't working anymore. So how is cutting-edge architecture dealing with these extreme geological conditions now?
We have to talk about Section 1.1, adapting to geological instability, specifically the research coming out of these high seismic zones. Think Taiwan, New Zealand, the Azores. They're working on something called ultra-deep geofracture foundations.
Right, and the traditional engineering playbook for that
was just pour concrete, pretty much. The playbook dictated that when you encounter fractured bedrock, you pour a gigantic concrete pad to resist it. You're essentially trying to bridge over the entire problem with just sheer mass.
The idea being, if the rock moves a little bit, your foundation is so massive and rigid, it just sort of ignores the micro movements of the fracture below it.
Exactly. It's brute force resistance. But the new philosophy is what they call adaptive engagement. So instead of fighting the naturally fractured bedrock, we work with it.
Work with the weakness.
Precisely. The briefing details this technique of drilling what they call micro-anchorage fingers.
Okay, can you elaborate on that? How do these fingers, how do they differ from standard piles or caissons?
It's a great question. A standard caisson is designed to hit stable strata, right, to transmit the load vertically down to something solid. These micro-anchorage fingers are much smaller in diameter, they're highly flexible structures, and they're designed to be drilled specifically into the fractured planes themselves.
Into the cracks.
Into the cracks. They don't try to bridge the fault. They key into the fractured structure. And by doing that, they distribute the structural load laterally, and they increase the foundation's lock by engaging the surrounding rock mass much more intimately.
That sounds completely counterintuitive.
Yeah.
If you anchor into the weakest point, the fracture, aren't you just making the whole structure vulnerable?
And that is the core misunderstanding that this new research completely overturns. The risk isn't the fracture itself. The risk is the concentration of stress at the fracture opening when a rigid structure tries to bridge it. The engineering challenge, and this is the key insight here, is developing a specific footing to geofracture interface plate.
Okay, so this plate is the critical intermediary. It's the translator between the building and the fractured earth.
Precisely. This interface plate has to be designed with materials and geometries that distribute the building's load without creating a new stress riser right at that pre-existing fracture. If that plate is too rigid or too small, it concentrates all the stress at the opening. And that acts like a hinge when the next seismic event occurs, which basically guarantees failure.
Wow. So what's fascinating here is that subtle shift. We've moved from just brute force material volume
to a highly detailed, nuanced material interface design. We are now engineering the relationship between the built environment and the geological environment at, a millimeter scale.
And that same attention to millimeter scale nuance, it applies equally to the skin of the building. Which brings us to Section 1.2, facades, as thermal and light conductors.
Right. We're looking at the deployment of semi-transparent thermal aerogel cores in facades, and particularly in pilot projects across equatorial megacities. So think Jakarta, Lagos, Recife. These are places defined by intense solar gain and just crushing humidity.
And the problem in those areas is twofold, right? You need daylighting for human well-being and to cut your electrical load. But you absolutely cannot tolerate the solar heat gain that comes with traditional glass.
Correct. And aerogel, this synthetic, porous, ultralight material, it offers a dual function that traditional materials just can't match. It acts as an incredibly efficient thermal resistor, so it dramatically reduces peak heat gain. But because of its structure, it also allows diffuse daylight penetration. The wall becomes simultaneously a superior thermal shield and a light conductor.
That sounds like the perfect material, which, that has to mean the practical pitfalls are enormous. What's the material science challenge that determines its failure point?
It's all about managing environmental chemistry. The critical technical challenge is preventing internal condensate from forming within the aerogel. See, aerogels get their spectacular insulative properties because they're mostly air-trapped within this delicate silica network.
And water vapor just ruins that network.
Completely. The moment high humidity drives condensation and water forms inside the aerogel's porous structure, its insulative performance, its R value, it just plummets immediately. You go from having this revolutionary material to just expensive, ineffective foam.
So the deep lesson here is that in these climates, the wall isn't just a thermal barrier.
No, it has to be designed as a perfectly sealed chemical environment. The section detail, the vapor barrier, the quality of the seals, those are the true determinants of long-term structural efficacy.
Now let's scale up. We go from the building skin to the entire city in section 1.3. And this is where the brief redefines an architectural byproduct shadow as a critical asset. They call it tectonic shadow mapping.
This is a fundamental philosophical shift in civic planning. It's huge. Cities like Seoul, Abu Dhabi, and Phoenix are using these complex computational models to simulate city-scale shadow cartography. They're running predictive simulations to determine exactly how every new tower, hour by hour, alters the district-wide thermal loads.
So we're moving way beyond simple zoning laws that just dictate setback and height. We're actually regulating the thermal footprint of a building on its entire neighborhood.
Exactly. Shadow moves from being a simple geometric consequence to a quantifiable municipal resource. You are managing the urban heat island effect at scale by strategically placing shade. And the source material outlines this massive policy implication that follows. If you connect this to the bigger picture, it introduces a market mechanism into environmental impact.
Tell us more about that, a market mechanism for shade.
They're proposing a zoning amendment model where shadow allowances become tradable development credits. So if your tower is designed, maybe through its massing or orientation, to cast a valuable shadow that significantly reduces the heat island effect on, say, a major pedestrian plaza, for a quantifiable period of time, you gain a thermal credit.
And that credit could then potentially be sold to a developer whose building, by necessity, is adding a disproportionate thermal load somewhere else in the city.
It makes thermal governance economically quantifiable. It's genius. It forces developers to integrate the city's thermal well-being into their initial feasibility study, not just as a burden, but as a potential asset. This challenge demands that architects become, in a sense, expert climate economists.
Let's look at the materials side again. Section 1.4, and this is about how architecture is becoming a carbon recycler. It's forcing industrial change through what they're calling limestone reformation plants.
This is critical. It's directly addressing the emissions from the cement industry, which is a huge polluter. We're seeing tests adjacent to traditional cement facilities in high production areas. Think Italy, Indonesia, Brazil. And this concept completely flips the cement plant's identity from a notorious carbon emitter to a core component of industrial ecology.
Can you explain the chemical process the brief outlines? How are they taking kodo and turning it back into a building material?
So the process involves these mineral reformation reactors. They bind atmospheric or captured KROs into stable limestone pellets. They're essentially reversing part of the calcination process that creates cement in the first place. And the resulting pellets can then be reused in concrete production.
The chemistry sounds complex, but it seems like the architectural problem is actually in the logistics. How does the facility layout make sure this recycling is economically viable?
The logistics challenge is the integration. You've hit it exactly. The design can't treat the carbon capture and the cement batching as two separate facilities connected by some slow transport route. The facility layout has to seamlessly tie the carbon capture operations directly into the batching plant logistics.
So the architect is designing for the ecology of the process flow itself.
Precisely. The hot, often noxious carbon output from the adjacent plant needs to feed directly into the reactor's input, and the reformed limestone output has to feed directly into the cement mixer outputs. You're minimizing energy loss, minimizing transport costs. This demands a mastery of architectural integration with industrial ecology, where the building envelope and the internal layout are driven entirely by material throughput and chemical reaction efficiency.
That discussion sets the stage perfectly for Section 2. This is where we leave the macro challenges and dive into the hyper-specific, often invisible forces. Chemical, thermal, acoustic, kinetic, all the forces that modern building programs introduce. This is where we really learn which structural assumptions have to be rewritten.
And this section analyzes 10 phenomena. They're highly specialized, often unseen, but absolutely catastrophic if you ignore them. Let's start with the unseen loads of air and chemistry in 2.1. Why is air chemistry now considered a structural load path, specifically in the context of chloramine corrosion drift in aquatic centers?
Right. When most people think of a pool structure, they think of water weight, humidity, maybe seismic load. They don't think of the chemical vapor itself as a load.
And that's the deep lesson here. Air chemistry, governed by thermal stratification, is a structural load, chloramines. These are the volatile compounds produced when chlorine interacts with organic matter, sweat, oils. They're heavier than air, but they get driven upward very quickly by the warm, humid air rising off the pool surface.
So they condense where the air cools, which is usually going to be the highest point of the structure, the roof.
Exactly. They rise, they settle, and they concentrate near the cool surfaces of the roof structure. We're talking the long-span steel trusses, the connection plates, and these compounds are highly corrosive. Over years, this uneven, concentrated chloramine drift causes accelerated long-term corrosion and deflection in the most critical structural elements supporting that roof. If you're designing a long-span roof over a pool, you now have to model chemical stratification as rigorously as you model snow or wind loads.
That is a staggering level of integration required. Now let's look at aerodynamics in a different context. High-rise safety. Evacuation cycle pressure pivots in government towers. We're talking about kinetic forces impacting emergency mechanical systems.
This deals with stairwell pressurization systems, which are, your last line of defense against smoke spread. The system works by actively blowing clean air into the stairwell to maintain a higher pressure than the adjacent floor plates, which keeps smoke out.
But during an emergency, the occupants are actively fighting that system.
That's the problem. When hundreds or thousands of people rush down the stairs at the same time, opening and closing doors, that mass movement of air and kinetic energy forces the pressurization systems into highly unstable states. They're no longer maintaining a steady pressure differential.
And the risk here is what they call the transient pressure reversal.
Correct. The momentum of the crowd and the abrupt cycling of doors can momentarily cause the high-pressure side, the stairwell, to drop below the low-pressure side, the smoke-filled floor plate. And that brief reversal is enough to suck smoke into the critical evacuation route. The engineering solution requires incredibly sophisticated tuning of the sequence of operation and fan response to stabilize against these kinetic and pressure loads imposed by the crowds themselves.
Okay, let's shift focus to vibration and acoustics in Section 2.2. In art schools, the brief highlights the need for practice room transmission vector mapping.
Oh.
Why is simply using thick, high STC-rated walls not good enough anymore?
Because typical insulation only deals with airborne noise sound traveling through the air. It does not stop flanking paths or structure-borne vibrations. Music rooms, especially for percussion or low brass, generate these dominant harmonic frequencies that travel not through the air, but through the solid structural skeleton of the building itself. The structural joist cavities, the slab edges, the shear walls.
So if you isolate the wall surface perfectly, but the joist runs continuously from one room to the next, that joist cavity acts as an acoustic corridor, just carrying the vibration right through.
Exactly. The lesson here is profound. Structural cavities have to be engineered as acoustic corridors, and the assemblies must be actively tuned, not just passively insulated. You have to map the vector, the direction and intensity of that specific frequency traveling through the structure, and then you have to introduce physical brakes or tuned dampers in the load-bearing path to interrupt that energy.
And this concept of subtle vibration impacting operations is just as critical in lab environments, specifically with fume hood resonance flanking.
This is a really subtle safety issue, but with major ramifications. Fume hoods are life safety devices. They're designed to maintain a consistent air velocity at the hood face, the safety threshold, to draw hazardous fumes out.
And if that air velocity dips, the worker's exposed.
Right, so if vibrations from adjacent equipment, say a powerful HVAC unit, a nearby centrifuge, or even a localized structural movement, if those vibrations flank into the hood zone, they can alter the air velocity consistency. That's resonance flanking. It compromises the safety threshold by introducing turbulence or fluctuations in the airflow that make the hood unreliable. It requires isolating the fume hood structure completely, often on its own independent vibration dampening pads, separate from the primary structure. And it requires strict mechanical zoning to prevent heavy equipment from being located anywhere nearby.
Moving on to section 2.3, thermal extremes. This brings us to a phenomenon that is entirely unique to modern electric vehicle infrastructure. Thermal runaway slab uplift in EV charging garages.
New building programs mean entirely new structural assumptions. It's that simple. We have always calculated static loads, the weight of the car. Fine. Now we have to calculate extreme thermal loads caused by a failure. When an EV battery fails and goes into thermal runaway, it releases a massive amount of heat incredibly quickly.
And that heat somehow becomes a physical load.
Yes, because it superheats trapped air pockets beneath the slab or within joint cavities. Think about heating a small volume of air in a confined space. The pressure just skyrockets.
So it's like a pressurized balloon under a thin layer of concrete.
Precisely. That rapidly expanding superheated air pocket causes the thin concrete slab, particularly near joints or seams, to lift and segment. This phenomenon, slab uplift, must now be engineered for. It demands revised joint detailing, pressure relief valves integrated into the sub-slab drainage layer, and potentially segmented thicker slabs in high-risk charging zones. The heat hazard from EVs is literally reshaping subterranean structural design.
And the inverse of that seems to be the chemical load from cleaning protocols, which brings us to wash-down slab infiltration tolerance checks in food processing facilities.
This is a classic example of operational requirements destroying long-term structural integrity. Food and beverage processing facilities have to adhere to these incredibly heavy, frequent sanitation cycles. They use aggressive chemicals, caustics, acids, sanitizers, and huge volumes of water during washdown.
And all that water and chemical solution just soaks into the slab joints.
If the slab joints aren't designed with extreme tolerance, that chemically saturated water infiltrates down to the structural steel, the rebar. The chemicals then degrade the rebar cover, leading to premature corrosion, structural expansion, and cracking. The building is literally compromising its own structural integrity every single time it performs a mandatory hygiene cycle. Successful design demands that the chemical load from industrial hygiene is treated as a severe, continuous structural load. That means specialized polymer joint systems and monolithic-grade slab finishes.
Finally, in section 2.4, we examine kinetic forces involving water, wind, and movement. Let's analyze amenity deck slosh modeling in mixed occupancy towers.
This is a very sophisticated dynamic load problem. High-rise towers inherently sway in response to wind and seismic activity. That swaying is usually predictable, it's within tolerance. However, when you introduce large, shallow bodies of water, rooftop pools, extensive amenity decks, the water mass is dynamic.
So the body of water isn't a static weight, it's a liquid, it moves.
It oscillates. The wind-induced sway of the building amplifies the slosh motion of the water in the pool. And that moving water mass, in turn, imposes changing dynamic horizontal loads back onto the structure. If the slosh frequency aligns with the natural frequency of the building, you get resonance. And that means massive, uncomfortable amplification of building sway. This is why major high-rises sometimes use dedicated slosh tanks, large water reservoirs specifically designed to actively counteract the movement. Rooftop pools introduce the same engineering complexity, just with a recreational intent that needs precise modeling.
Next up, balustrade vortex uplift in large civic atriums. The idea that vertical air channels could actually lift a structural element is genuinely surprising.
It really highlights how vertical geometry creates unexpected dynamic air currents. In multi-story civic atriums, the stacked effect, the natural movement of warm air rising, is enormous, so air currents rush upward along the edges of mezzanines and balconies.
And the geometry of that vertical face creates a vortex.
That vertical airflow generates an unexpected pressure differential, and that results in significant upward pressure or uplift load on the glass balustrades. Architects typically design balustrades for horizontal impact, a person leaning on them, or vertical dead load. They must now account for significant lateral and uplift loads caused by the building's own internal vertical air channels. Ignoring this can lead to failure of the glass anchorage or the glass assembly itself.
And our last example in this dynamic section is landside microclimates interactions at regional airports. This involves wind, water, and subsurface temperature dynamics.
A seca is a standing wave in an enclosed body of water. Here, it's a microclimate occurring on landside pavements. Wind blowing across large, shallow pools of water on irregular pavement creates these subtle, oscillating water movements.
But why does oscillating shallow surface water matter to the subsurface foundation?
Because that subtle, continuous oscillating movement profoundly alters the thermal dynamics of the soil. And, critically, the foundation frost layers below the surface, particularly in cold regions. See, static water insulates, but moving water carries heat away more efficiently or transfers cold more quickly. The uneven freezing or thawing cycles caused by these microclimates create long-term foundation instability. The deep lesson is that even shallow surface water, if it's allowed to pool and move, can alter subsurface temperature dynamics enough to compromise the foundation integrity over years.
The lesson of Section 2 is pretty clear. The building structure has to quantify every single force acting upon it. Section 3 forces us to internalize that lesson by treating a building's operational rhythm, its daily use, its workflow, its emergency cycles, as quantifiable physical loads. So let's examine some specific construction management, or CM, scenarios.
We'll start with a classic industrial clash in Section 3.1, vibration spike harmonics in a medtech plant. The scenario is clear. A new high-throughput packaging line is installed. It's operating at a frequency of 21 to 28 hertz. But the adjacent precision microassembly benches, which are where the billion-dollar products are made, require a vibration tolerance of less than 15 hertz.
So that clash translates instantly into product failure, calibration errors, and a massive loss of productivity. This raises an important question. In a live operating facility, how do you solve this engineering clash without shutting down the entire line for months?
The required workflow detailed in the brief is very instructive. It shows the integrated solution. Step 1 is a modal analysis of the slab plus the machine interaction. You need to understand how that 25 hertz vibration from the machine is traveling through the slab, which is often amplified if the machine frequency aligns with the natural frequency of the concrete slab itself.
You identify the problem source and the path first.
Exactly. Step 2. You tackle the source directly by installing tuned mass dampers, TMDs, under the offending packaging machinery. And these aren't just rubber pads. They are precisely weighted and tuned systems designed to oscillate out of phase with the machine's dominant frequency. They absorb and cancel that 21-28 hertz vibration.
And then you protect the receiver, the assembly bench.
Step 3. Introduce sophisticated isolation pads beneath the assembly benches, physically decoupling them from the vibrating floor. But the final, and this is the often overlooked step, is step 4, relocating lightweight partitions.
Why the partitions? They're just drywall or aluminum framing.
But they're acting as unintended harmonic transmission plates. They're lightweight enough that they don't absorb the vibration, but they are rigid enough to transmit that 25 hertz harmonic wave right across the room to the assembly benches. Removing or replacing them with acoustically decoupled walls prevents that structural flanking. The lesson here is that manufacturing rhythm is a structural variable. Operational loads have to be treated and mitigated like continuous physical ones.
We see that same principle applied to thermal stress in Section 3.2, with a focus on data centers and thermal gradient beam torsion. Data centers are defined by their heat output, and apparently that heat is literally twisting the structure.
The scenario is high-density rack containment. A data center installs new hot aisle containment, which means they isolate the exhaust air from the intake air. And this leads to huge, non-uniform temperature profiles on the supporting structural steel. In the example, they found a 13 degrees C differential between the top and bottom flanges of a 36-inch steel girder.
When steel gets hot, it expands. If one side is 13 degrees hotter, that expansion is uneven, and that causes torsion or twisting.
Precisely, and the risk is immense. You're talking about rack alignment errors, which cause catastrophic IT failure, cable tray bowing, stress on the raised floor pedestals. A differential that large can result in several millimeters of torsional twist over a span, which is just unacceptable in environments that require sub-millimeter precision.
So how do architects and engineers mitigate this heat-induced structural deformation?
Again, the 4-step workflow provides the blueprint. First, you rigorously model the torsional load from the thermal gradients in the design software. Second, you add thermal barrier shielding, so reflective coatings or insulation, to the hot side of the beam to reduce heat absorption. Third, you integrate specific torsion-resisting bracing at the midpoint bays of the girder, which forces the beam to hold its alignment. And finally, you adjust the containment geometry and the cooling infrastructure to equalize airflow around the structural elements, minimizing the differential in the first place. The lesson is undeniable. In high-density data environments, heat is structure. Thermodynamics become a fundamental and continuous part of the load path.
Moving to section 3.3, we're addressing human operational loads during emergency and crowd dynamics. Let's start with emergency cycle mechanical surge torque in hospitals.
Hospitals are required to perform rapid state changes. During a code blue or some other intense medical event, mechanical systems, HVAC, specialty venting, pneumatic tube systems, they have to change their operational state instantly. They often have to move from standard airflow to maximum capacity or even reverse flow in a split second.
And that rapid mechanical change, starting and stopping massive fans, reversing dampers, that creates a physical force.
It creates significant torque spikes in the duct risers and mechanical shafts. Engineers traditionally design for a steady state, constant operational load. But these emergency cycle surges impose instantaneous mechanical loads that exceed the normal operational design, and that risks damage to duct hangers, fasteners, and even the shaft structure itself, unless the system is explicitly designed for the extreme, transient forces generated by emergency behavior.
And in governance facilities, the load is generated purely by people and politics. Policy cycle occupancy surges.
This is all about program-driven egress modeling. A governance facility, a parliament building, a major courthouse, a municipal center is typically half empty. But legislative events, high-profile public hearings, or major policy announcements, they produce abrupt crowding and extreme, unpredictable egress demand.
So the flow isn't steady. It's a surge driven entirely by the political calendar.
Exactly. You can't design for the average number of cubicles. You have to design for the political and media cycle. And this demands flexible routing and program-driven egress modeling that accounts for maximum crowd behavior under stress. It often mandates redundant, high-capacity egress routes that sit unused 90% of the time simply because that 10% policy surge could lead to a catastrophe. And this affects planning feasibility studies fundamentally because you're spending significantly more on underutilized egress infrastructure.
Finally, in section 3.4, we look at life safety as an active management problem. Let's start with the requirement for active construction fire watch, which is required by the IBC, the International Building Code, section 3305.
This deals with the construction paradox. New structures are highly vulnerable because high-risk combustible materials, insulation panels, specialized adhesives, large quantities of lumber are all being installed before the permanent fire suppression and alarm systems are active.
So the site is at its maximum risk but has minimum protection.
Correct. And the brief emphasizes that continuous monitoring by temporary fire watch teams is required during this vulnerable phase. And crucially, because of the severe vertical flame spread potential when facade materials are being installed, elevated work platforms require specialized, dedicated fire watch assignments. The key takeaway is recognizing that incomplete life safety systems are themselves a temporary hazard that demands active, full-time mitigation management.
And that active intelligent management concept is also mirrored in the shift toward distributed notification logic under NFPA 72 for large multi-atrium complexes.
We are moving away from the loud, monolithic, building-wide alarm, the horn that just blares everywhere instantly. In complex buildings, that just creates chaos and impedes emergency response. Life safety has to be zonal, not monolithic.
How does that zonal, intelligent choreography improve the outcome?
It sequences the alarms based on smoke zone logic. So if smoke is detected in Zone A, the lowest floor atrium-only adjacent zones are immediately alerted, and potentially with localized voice command systems that direct evacuation away from Zone A. Crucially, this localized choreography prevents responders from encountering a massive, disoriented crowd. It preserves critical emergency response corridors, allowing first responders to access the incident location quickly without the building-wide rush. It's intelligent alarm choreography that prioritizes egress and access.
We've thoroughly quantified the invisible forces, from chloramine drift to thermal torsion, that define the structural loads of the future. Now, in Section 4, we connect these microforces back to macrovisionary design and large-scale civic planning. The building itself is becoming a sensory organ for the city.
And starting with Section 4.1, computational democracy in participatory zoning. This is architecture connecting directly to the political process.
The brief notes that cities in India, Kenya, and Vietnam are deploying these AI-mediated zoning platforms, and the community's voice feeds real-time simulations. Planning is transforming into computational democracy.
The ideal outcome is just staggering. Citizens can propose a zoning change, say converting a derelict lot into mixed-use housing, and the AI instantly simulates how that change impacts noise levels, mobility patterns, resource distribution for the whole surrounding district.
So they see the trade-offs immediately, which makes the political negotiation transparent and data-driven.
It creates instant feedback. However, the critical challenge is not the simulation, it's the governance. We need to propose a data-to-policy decision chain, one that ensures that compelling AI-mediated citizen feedback transforms into legally enforceable zoning refinements. How do you bridge that gap between a compelling, data-driven simulation and actual, immutable municipal law? This requires architects and planners to integrate legal counsel right into the design phase.
That concept of responsive intelligence is also being baked directly into the physical form of the building itself, which is detailed in the design prompts in Section 4.2. Let's look at the first one, the Equatorial Light Filter Institute.
This prompt demands a building that actively and visibly manages the intense solar environment. The design has to modulate solar intensity using layered, semi-transparent materials, and the deliverable requires 3 distinct functional material layers, one for structural support, a light-scattering substrate, and an outer layer for humidity-resistant shielding.
The constraint forces structural expression. The daylighting must be diffuse, never direct, and the structure itself must visibly express the filtering concept. The architecture has to tell the story of its own climate management.
It's an elevation of the facade from just a simple weather envelope to a dynamic, functional piece of atmospheric infrastructure. Now, the second prompt, the Atmospheric Intelligence Annex, pushes this concept even further.
This is a municipal annex that has to sense, interpret, and display citywide atmospheric data humidity, wind direction, particulate concentrations, but with the fascinating constraint that it must avoid digital screens entirely.
The structure has to use mechanical or material transformations so the public can read atmospheric conditions intuitively. The building becomes a giant analog sensor. For example, maybe the facade uses bimetallic materials that visibly shift or darken based on temperature and humidity levels. Or perhaps a series of louvers physically rotates to align with or oppose the dominant wind direction.
So the architecture is acting as a physical data visualization tool. It's making invisible environmental data legible to the pedestrian public. That is true civic intelligence.
It's the ultimate expression of architecture as public service. You're bypassing the complexity of a digital interface to make environmental awareness immediate.
Now moving to Section 4.3, we see infrastructure blending into transit stops. The concept of adaptive modular canopies for bus rapid transit or BRT corridors is shifting transit stops from simple shelters to active micro-infrastructure nodes.
We're seeing this implemented in high rainfall cities like Bogota, Kigali, and Manila. These modular canopies are engineered to adjust their tilt and length during heavy rainfall events. And they aren't just for keeping passengers dry, they're actively channeling massive volumes of runoff.
And that channeled runoff is being used to generate power with energy generation microturbines.
Exactly. The transit stop is generating its own operational power from the resource it intercepts rain. The design intricacy here is phenomenal. You're designing a hinge and drain geometry that simultaneously optimizes the water flow rates needed to spin a turbine efficiently, while also maintaining pedestrian comfort by preventing massive sheets of water from splashing down onto the waiting area. It demands a holistic integration of hydraulic engineering and human factors design at the smallest scale.
And here's where it gets really interesting. Finally, we arrive at the definition of resilience architecture through the Continental Emergency Resilience Laboratory Project, or CERL.
This is perhaps the most strategic project outlined in the briefs. CERL is proposed as a multi-state campus focused on disaster prediction, evacuation modeling, structural hazard simulation, and high-level policy training. It is architecture as a proactive defense mechanism.
This project demands integrating structural risk, civic governance, and mobility modeling into a single, cohesive, living campus. It has to physically embody resilience.
The vision is to position CERL as a continental nervous system architecture that senses, predicts, and coordinates multi-state emergencies. But the core architectural challenge is circulation, security, and functionality overlap.
Why is circulation so challenging here?
Because you have three fundamentally disparate user groups operating on the same campus, often at the same time during a crisis. You have the public participating in training and education. You have high-security scientific research labs requiring sealed vaults and restricted access. And you have executive decision-making centers where governors and policymakers meet.
And they absolutely cannot overlap. A scientist can't accidentally walk into a high-level executive briefing.
Correct. The architects have to define a circulation strategy that integrates all three functions seamlessly. It has to ensure maximum operational efficiency during a simulated or actual emergency while eliminating any security overlap. The architectural geometry must physically manage the hierarchy of access, security, and emergency coordination simultaneously, often through complex vertical and horizontal separation zones that only merge at designated high-security command centers.
This has been an incredible survey of the field. We've moved from foundations that adaptively engage with fractured rock and walls that chemically manage light and heat, through highly specific operational loads like chloramines and thermal torsion, and finally to architecture that serves as civic and atmospheric intelligence.
The core lesson we take from the daily Mentorship Digest is clear. Success in the built environment of the future demands that we anticipate and quantify 5 essential dynamic variables: structure, air, water, heat, and vibration, in ways that fundamentally exceed traditional static analysis. Buildings are no longer inanimate objects. They are dynamic, sensitive participants in the environmental and political life of their region.
And this knowledge isn't just for a world-renowned firm. It's about shifting your own perception of what a building must do. You are now aware of the microforces, from acoustic harmonics to micro-CT interactions, that can determine a project's long-term viability and success.
So what does this all mean? It means the definition of architecture has fully expanded to encompass fluid dynamics, advanced thermodynamics, industrial ecology, and political science. It's no longer just about geometry, it's about synthesis.
And this leaves us with the reflection prompt posed in the source material, a challenging concept for you to mull over as you observe the built environment around you. How does invisible environmental intelligence become architectural intelligence? Think about the structural integrity of the truss above the swimming pool, or the quiet twisting of the steel girder in the data center, and consider the building's role as a sensory organ for the city.